Good morning, everybody. Today we have the presentation with Mahdi Safarpour from a PhD student from the University of Antwerp. Okay, Mahdi, you can start.
Okay, so thank you so much. So first, let's say good morning, everyone that are joining this, let's say, session from Peru, from the Cayetano University. So as a brief introduction, my name is Mahdi Safarpour, and I'm PhD student at the University of Antwerp. So I joined the group of Global Health Institute about 3 months ago, and I'm working on, let's say, the main topic of my PhD thesis is about, of course, malaria, but my main focus is on working on to understand what's the effect of human mobility on persistence of malaria in Amazon jungles in the Peru. So I choose this article because I found it very relevant to the topic of my PhD, because also in my PhD thesis, I'm looking for a way to find and distinguish between the local, let's say, infections and the imported infections, and the way that we can integrate the data of the genetic data of the parasites, and of course the other type of epidemiological data, in order to understand okay, what's the origin of the infections and if we can detect the imported cases. So that's why I chose this article, as it's mentioned in the title. So the aim was to mapping imported malaria in the Bangladesh using those parasite genetic data and the human mobility data. So as I have about 14 minutes to present this article, so I think the best thing that I can do is to have a quick overview of the abstract and the introduction, and then we quickly overview the methods and spend most of our time, I think, for the result and the discussion. So first, let's start with the abstract. So it's mentioned that in order to eliminate malaria, so we need to implement different interventions, or let's say implement national control programs to be able to eliminate malarias. But the recent evidences clearly show that there is a problem that we must take it into account, and otherwise it demolish all our efforts in order to eliminate the malaria. And that's the travel of infected individuals between endemic areas. So therefore, we always need to find a way to quantify parasite importation, or let's say transmission, from one endemic region to another endemic regions. So in this study, they used 4 different types of data. The first one was epidemiological surveillance data. The second one was the travel service data. The third one was the parasite genetic data. And lastly, they used the mobile phone data in order to measure the spatial spread of malaria parasites. So the setting that they used was the southeast of the Bangladesh. And the researchers used, let's say, 2 different statistical methods in order to answer their research question. In one hand, they used only the parasite genetic data in order to develop a genetic mixing index. We will see more about it in the next pages, but they developed a genetic mixing index that estimates the likelihood of samples being local or imported. On the other hand, they use the travel surveys data and the mobile data, integrating them into the epidemiological models in order to have an estimation about the direction and intensity of the parasite flow between the locations. So based on, let's say, their methodology and the data that they had, the result indicated that there is a clear evidence of heterogeneous transmission outside the high incidence forested area to the, let's say, the area with less, let's say, dense of forested regions. And they also found that found substantial importation of parasites through, let's say, southeast of the Bangladesh to the other parts of the regions. So as a brief introduction and have a clear idea about what they were looking for to do, let's go through the introduction that provides more information. The introduction is in 2 pages, but Let me just summarize the most important point. The first point is that it's mentioned that in elimination and pre-elimination settings, we must always take the malaria transmission into account, because otherwise we will not be able to eliminate the malaria in the endemic regions. So it's mentioned that most, let's say, national control programs, the main focus is on reducing transmission or control the imported infections in order to make sure that let's say, the interventions that we are implemented are efficient enough to eliminate the malarias. The next point that's mentioned in the introduction is that how we can, let's say, eliminate malaria in an endemic regions. Of course, the answer to this question is quite clear and obvious, and that's that we need to apply or implement different interventions. But the main question is that how we can make sure that our intervention is efficient enough to eliminate the malaria in the endemic regions. So to be able to have an idea about the efficiency of let's say, the interventions that we implement in endemic areas, we need to have a clear idea about the pattern of travels to and from malaria endemic regions. We must know that, okay, what's the rate of traveling from one endemic regions to another endemic regions? What are the direction of the traveling from one zone to another zone? And at the same time, the density of the, let's say, the travelers that are moving from one region to another regions. The next point that is mentioned in the introduction is that, however, everything looks like very easy, but there are still some challenges. And the main challenges that we have in such a study is that measuring the spatial spread of malaria remains technically challenging because of so many reasons, but they mentioned two of them in the introduction. One of them is that we always faced asymptomatic and undetectable infections. As mentioned in this article, they just, let's say, use the symptomatic people in their study and not asymptomatic people. So that's one of the challenges that we always face when we talk about, let's say, the malaria elimination. The second point is, let's say that when we talk about the epidemiological surveillance or the travel surveys, it's always difficult to implement, let's say, travel surveys in remote areas. And at the same time in, let's say, highly mobile population. So in the remote areas, most of the time we do not have enough infrastructures to be able to, let's say, collect the data, the travel surveys or the epidemiological surveillance. And next point is that if we have a region with, let's say, highly mobile population, it's not really easily to distinguish between the local and imported transmissions. And however, some models may enable to distinguish between the local and imported transmission, but there are a lot of evidences showing that such models are not able to accurately capture the differences between the imported and, let's say, the local cases. So the introduction also provides some solutions for the challenges that we mentioned. One of the solutions is using the mobile phone data and integrating the mobile phone data into the epidemiological models in order to have an estimation about the source and sink of parasites and the impact of travels on the spread of malaria. But the point is that using the mobile phone data is not applicable in, or let's say, feasible in all settings, because in the regions with the low cell tower density, it's not applicable to use the mobile phone data. So it was one of the solutions mentioned in the introduction. Another solution is use the parasite genetic data, but it also has its own challenges. The first challenge is costs. So we need a good source of, let's say, financial means to be able to use the parasite genetic data if you want to distinguishing between the local infection and imported infection. The second point is that in a low transmission setting, it's been shown that we always face frequent combination of recombination of parasites. Therefore, the genetic data that we use or the genetic signals that we use in such studies may not be good be enough to distinguishing or resolve between the imported and the imported cases and the local cases. And the next issue that is mentioned in the introduction that was also interesting for me, was the lack of appropriate methods for analysis. So it said that there are several methods that we can use, but the point is that most of them are based on the assumptions that are not always met. So, however, there are some methods that we may use, but we still need to interpret the result with cautions. So the introduction and with the goals, and the authors mentioned the main goal, the goal of the study, which was developing a method that gave us a better insight from genomic data, using genomic data, epidemiological information, and mobility data in order to be able to understand and distinguish between the imported cases and the local cases. And they mentioned that based on the result that they could find, we can implement this result in the surveillance workflow and support the decision-making for the control programs. We can see, for example, for the things that we can see in the proof. So after talking about the abstract and the introduction, first, let's go quickly to check the methodology. I don't know if everyone can hear me clearly. Just I want to make sure that
yes, we hear you. We hear you.
Okay, good.
Maybe you can increase a bit also the font.
Oh yeah, of course, I can increase the fonts. So yeah, that is the discussion. It's in page 13. Okay, let's see. So about the material and methods, let's say they use patient self presenting, let's say, reports from 58 health facilities. They collected data from January 2015 to September 2016. They only use the tested positive people, both based on the rapid case and let's the microscopy test. And in total, they could collected the data of about 2,000 individuals. And the point is that they divided the infection based on the type of parasites, but the majority of was falciparum, and the next one was the Vivax, and they also reported some mixed infections, and they had 3 cases that were unknown. So they use the data of, let's say, the travel survey to have an idea about, let's say, the trips that happened between the regions, and they divided they quantified, let's say, the trips into 4 main categories. They divided to the work, frequent, infrequent, and forest. So forest means those who travel to the forest. Work, of course, means the people who travel to their workplace, and frequent and infrequent refers to the number of time that the people and individual travel between 2 different, let's say, they call it unions, but we can also call it the regions. So the next point is that they have in total 176 unions, or let's say the regions. They use the mobile phone data from April 1 to end of September. So I don't have any clue why it's not in line, let's say, with the time that they collected the data of individuals tested positive, because they collected the data of the individuals from January 2015 to September 2016, but they collected, let's say, the data of the mobile data a year after. So, but anyway, this is the way that they run their study. So as it mentioned earlier, the confirmed cases are the cases with the positive result of microscopy and rapid test. So the next issue that we can mention about let's say, their methodology is that so to have an idea about the percent of the forest coverage, they calculate it based on the method that's mentioned by Hansen et al. To see that which area of the Bangladesh or southeast of the Bangladesh can be considered as, let's say, forest region or the non-forest region. And interesting point was that they also use an R package to be able to estimate the geographical distance between, let's say, or the road distance between two different units. So this is the general information about their samples, the number of samples, and the way that they collected their samples. For the genetic data, they use the genetic barcodes of, let's say, about 1,400 individuals from 134 different units. And in total, they use 101 SNPs, the data of 101 SNPs into their models. So as it's mentioned earlier, so they use genetic mixing index to have an idea about whether what to have an estimation about the heterogeneity of the genetic parasites in each units. So this is the formula. Maybe I should zoom it in a bit. So it doesn't look like to be a very complicated formula. As it's mentioned here, it's just a probability of genetic similarity between, let's say, the distance, whether the distance is far or the distance is close. So based on the genetic mixing index, they can have an estimation if a sample had a higher than expected probability of sharing genetic similarity with the samples far away, and then they concluded that it's likely that it was imported. Otherwise, they suppose that it's not an imported cases. And they could also calculate, let's say, the confidence interval for the genetic mixing index that's mentioned here. But they use their own cutoff to whether have a classification to see whether the genetic mixing index is high or not. So the cutoff is if the SNP differences that we observe is less than 75%, they assume that, okay, the genetic the possibility of sharing and mixing the genetic parasites from different unions is very low. And they suppose that if the genetic mixing index is less than 17.5%, they assume that these people's, or let's say, the parasites that we see are located in a distance less than 20 kilometers. But if it's more than 30%, if we see, in case we see a genetic index greater than 30%, it means that we are talking about, let's say, a parasite that's coming from a very far distances, and that's be used as an indication that, okay, what we see in our union or our region doesn't belong to that region or the neighborhoods. And since it's coming from a place that is really far from that, the place that we're talking about, most probably these people is an imported cases and not the local case. In the following, they use, let's say, the method that they use to be able to find the association between the genetic data and the travel survey and the mobile data. So what they did was that comparing the genetic data with both population level and individual level survey data. So what they did was that they examined how changes in SNP differences can impact, let's say, the association between the genetic data and the travel surveys. So for population level data, they use 100 permutation as a kind of simulation to see what would happen in the different scenarios. But for, let's say, let me see, where's that? that is for the population level. And they had three different scenarios. That was the main point. Then they had three different scenarios. The first scenario was that the individuals living in the same unions or the regions, and they wanted to know what's the impact of, let's say, changing the ethnic differences in different scenarios in, let's say, the association between the genetic data and the travel surveys data. In the second scenario, they considered that the individuals coming from places with direct travels. And the last scenario, the third scenario, was that the individuals coming from places with indirect travel. So based on these three different scenarios, they had three different models indicating that we will see the result very soon, that, okay, what would happen in these three different scenarios. But they also have some notations that how they calculate it. I found it a bit difficult and mathematical, but if we go to the results are much easier to interpret than what we see here. Let's say as a formula. I don't know if we have any biostatistician among us that can tell us more about this later, but yeah, anyway, this is the way that they use. We will see it in figure 2, but this is the way that they reach to the results in the figure 2. They also, but the main point is that in this paper, they always separate the data of the mobile phone data with the survey data, and always compare the models that are created based on the mobile phone data and the survey data. And sometimes they combine both of them together to see what's the added value of using both mobile phone data and the survey data. So it was about the individual levels and it was about the population levels as mentioned here. They also did it in, let's say, individuals level that is mentioned here. Let me find it. Yeah. Okay. They also did it in the individuals level, but let me see, where is that? Okay. Oh, okay, yeah, it's here. When we talk about the mobile phone data, they always think to talk about individuals level data analysis, but when they talk about, let's say, the surveillance, they talk about the population level data. There are also some points that they mentioned in their paper that are not really clear for me, so maybe we can discuss it later. But for example, one of them is that at individuals level, they have a, let's say, a formula that's located, that shows as odds ratio, and it shows that the residence location or the travel patterns, it's based on the residence location or the travels patterns. So it said that the nearly identical barcodes, it means the genetic barcodes, are those with less than 10% differences, and not nearly identical genetic barcodes are those that we see the SNP differences in 25th and 75th percentiles. So if we calculate the odds of nearly identical barcodes compared to not nearly identical barcodes, then we have an idea about the people that is belong to that union, or is important cases that travel from one union to another union. So, and they have also some examples or justification that is not really clear for me, but maybe we can discuss it later. For example, it said that the expected pairwise similarity between two random parents is 0.558, and therefore the expected parent offspring similarity after one outcrossing event is 0.779. So again, if there is anyone that can explain it, it would be really great, because I tried to find what's the logic behind this, let's say, formula, but couldn't find anything. So the next point that they mentioned their methodology is quantifying the probability of a geographic distance with a given SNP difference. So in order to investigate the relationship between geographic and SNP distance, they divided, let's say, the region or the setting of the study into the 7 geographic distance windows. So the first windows, as we see, is 0. The second one is between 0 and 10 kilometers, and so on till we reach to the, let's say, the last windows, which is greater than 100 kilometers. They also divided the SNP differences into 6 different categories, whether there is no SNP differences, that's mentioned in the zeros, and then between 0 and 10%, and go on till we reach to the differences between SNPs between 30 to 35%. It refers to the, let's say, the SNP differences that we see between 2 different unions. So if the SNP differences is 0, so it means that these 2 unions are identical. But if the differences increase, it means that, okay, most probably these unions are not very close to each other. They are very, let's say, separate and distinct regions located far from each other. So they try to see whether bringing these 2 information together, I mean, let's say the geographic distance windows and S6 and SNP differences, can we find any association between these 2 elements? So what they did was that first, as it mentioned, the main idea was to see whether the genetic distance can give us an idea about the spatial relationship and the distance that we may see. And they used, let's say, the Bayes rules to be able to somehow estimate that whether based on the SNP differences, is it possible to have an idea about the distance that we see. The formula does look very complicated, but I expected to see more information, but unfortunately the authors just provide, let's say, general overview of the formula that they use. And even in the results, there is not much information about, for example, the result of these sections, but at least to give you an idea, what they did in this section was that they wanted to know that if it's possible to have an idea about how far 2 unions are far from each other, just only based on SNP differences that we may find in different unions. Yep, so now we reach to the modeling parasites flow using tribal survey and mobile phone data. So they calculate the number of trips between all pairs of unions. So this is another point that was interesting for me, because they have about 170 unions, but to be able to detect, let's say, the direction of the travel from one union to another union, they just use the pairs of unions. They didn't look at the unions as a network. So that's another interesting point for me, but I couldn't find any justification why they did not look at it as a network, but they decided to look at it as a pairs of unions. So this is another point that we should keep in our mind, that they look at the unions as a pairs of unions and not as a network. So they use both travel survey data and the mobile data. What they did, that, as mentioned, they use the data of 176 unions. And the next point is that in about 60% of the unions, there was at least one mobile phone tower, and they used the average number of trips over the 6 months. So that is, I think, another a good point that we should take into account. And the next point is that they normalize the number of trips. So for example, if we have 100 trips from one union to 6 other unions, so they didn't look at it as a numbers, but they normalize it based on, let's say, reported as a proportion. For example, if you have 100 travels from one union to another 6 unions, for example, 10% of them is to the union A, 20% of them is to union B, and so on. So again, I don't have any clear idea why they didn't use, let's say, the number, and they decided to look at it as a proportion. But yeah, anyway, this is the way that they did their analysis. And the last one is epidemiological estimates of parasite importation. So to be able to have an estimation about the parasite flows based on the travel from the residence unions, they used a scaled, let's say, index that was created based on relative incidence in the destination union versus their residence to have an idea about the parasite. Then they used a proportion of, for example, they estimated the proportion of infection in union number 1 that are coming from union number B to have an idea about, okay, about the parasites flow. So let me see. And again, they just considered the clinical cases and not the other cases. So if there is not any questions so far, let's go to the results section and then check the results. Okay, so everyone can hear me?
Yes.
Okay, good. So I think for the results, the best thing that we can do, we can go through first, let's say, the figures, and then we can go through the text to see more details. So this is the figure 1. So that shows the incidence of malaria and a spatial connectivity in Southeast Bangladesh. So the figure A shows the average monthly incidence per 1,000 population of falciparum from 2015 to 2016. So it's mentioned that the incidence is highest, of course, in eastern portion of the Bangladesh because this place is forested region, as shown in the picture. And the picture B, so it's just the picture B shows us the density of, let's say, forest coverage. So the places with, let's say, dark green are the places with more dense forest coverage, but they use a cutoff of 50% forest coverage to distinguish between forested and non-forested regions. So the places with forest coverage over 50% were considered as a forest region, and the places with the, let's say, density of less than 50% considered as a non-forest region. If we look at the figure, okay, this is the figure A, this is the figure B. So let me zoom out a bit. Okay, in figure C, what we see is that the unions sharing at least one parasite with identical genetic barcodes. And the next point is that what we see, we can clearly have a border between the north and the south. So as we see, there is no connection between north and south. In the closer unions, we can see that, okay, for example, these 2 unions are sharing at least one parasite with identical genetics. Or for example, these 7 unions located in the north area sharing at least, again, one parasite with identical genetics. But as we see, we can clearly have a border from north to south, and we see that there is no connection between north and south. In figure D, what we see is that the most traveled routes between per location. As I mentioned earlier, they didn't look at the locations or the unions as a network, but they rather consider it as a, let's say, pairs of unions. So what we see in figure D is that the most routes between each unions, that the data was collected from the travel survey data. So the figure D is rated based on the travel survey data. We see the same thing in figure E, but this time we see the most travel routes, but this time they use the mobile phone data. So again, an interesting point for me is that the figure D and the figure E, let's say we see two different picture of most travel routes. I expected to see almost the same result, but what we see is that not totally different, but is not, of course, not 100% identical. So this is just the preliminary results, giving us an idea about, let's say, the setting of the study, the most traveled routes, and the unions that are sharing at least one parasite with identical genetic data. So if we want to go to more details, I think there are also some interesting points that maybe we can discuss about. The first figure, for example, they find that when they use the travel survey data, in about 30% of positive individuals, they reported that they living outside forest areas. But the point is that about 66% of them did not report any travel to forested areas. So they suggested that maybe there is something that is not working very well. So the first assumption is that the travel survey did not capture all forest travels because of a lot of sorts of biases that we know we have in such kind of, let's say, self-questionnaire questions. And then next assumption was that the individuals were accurate infections outside these areas. So they couldn't distinguish what's the reason that they can see the infections in a people with enough evidence that they are traveling to the forested regions, but for any reason they couldn't capture it. This is one of the points that I find it interesting. The next point is that they somehow try to find a temporal association between the parasite pairs with identical genetic barcodes. Their main assumption was that if we find identical genetic barcodes in two different unions, most probably these two unions might be closer in time than those that we cannot find identical barcodes. And they mentioned the median here that was interesting for me, 6.5 versus 145 days. So it means that if we find identical genetic barcodes and we convert it, let's say, to the time, we will find 60.5. And if we find a parasite pairs with, let's say, highly inidentical genetic barcodes, and we convert it to the time, we find it 145 days. I mean, what I understood is that it refers to, let's say, the destination between the parasite pairs in each unions, and they try to have, let's say, as they mentioned, to have a temporal idea about what's the difference between these two unions in terms of the time. But I'm not so sure what these numbers refers to. When we talk about 145 days, I think, does it mean that the days that may take that one parasite from one union to another union, or what else? Because they didn't explain anything about what does it refer to. But I found it very interesting. Maybe I also use it in my study, because it's always good idea to, let's say, convert the destination to the time. And the use man-Whitney you test to see whether these two medians are different or not. So I think there is no more to add about the figure 1. So let's go to figure 2. Let me zoom out a bit. So as it mentioned, they had 3 different scenarios in order to associate the genetic data with travel survey and mobile data. So what they did was that they compared the genetic data with population level travel survey data and mobile phone data in 4 different scenarios. The first scenario is that the parasites belong to the same unions. The second one is that the parasites coming from the unions with direct travel reported in the travel surveys. The scenario number C refers to the point that parasites coming from the unions with high indirect travel. And the third one is that the number D is same as the number B, but the only difference is that they just consider let's say high direct routes, because there was a lot of, in their study they mentioned that there was a lot of high direct routes, but they just consider them consider the one that the most travelers are passing from them. So I read this article several times to understand what these figures exactly tell us, but find it very difficult in terms of interpretation. If we read the text, we find it clear enough what is it about. But when I look at let's say the figure, it's not really clear for me what is exactly referred to. For example, it's mentioned that let's say the red lines that we see are given thresholds, but I don't know what kind of threshold it exactly is and how they calculate it. This is the first point. The second point is that, for example, if we look at the scenario B, which is the proportion of pairs, it means parasite pairs from different unions with direct travel. I do not have any idea of why, when the SNP differences is almost 0, why it's 70%. So for me, it can be any let's say proportion or any percentages. I don't know if because they mentioned that they use a permutation as a kind of simulation. I don't know if this is the result of their simulation, and if we change the number of permutation, we may get a different results or not. So it's not really clear for me. It's not at the same time explained in the papers. And the next point is that if we look at the if we look at the gray, let's say lines, again, I do not have any idea what's it. The range is just between, let's say, 10% to 30%. Again, for me, it can be any number, but what they mentioned about the figure, let's say, that we see here, is that they try to somehow explain so the association between SNP differences between the pairs of parasites and the proportion of the parasites that we can observe from different unions, and of course different pairs of unions, because they just concentrate on pairs of unions in the 3 different scenarios. That is, okay, the parasites belongs to the same union in figure A. The parasites do not belong to the same unions, but 2 different unions, A and B, are connected together with a direct travel. And in scenario C, that is, let's say, indirect travel between A and B through C, of course. And again, in the scenario number D, that is same as B, but the only difference is that they consider the highly traveled route. So maybe if we have time, it's also good to discuss this figure to see what it exactly tells us. So let's go to, okay, the next figure, which is figure number 3 is not very complicated figures, hopefully not like figure number 2 that I found it too difficult to at least interpret, not the text, but the figures. So figure number 3 shows the relationship between the genetic and geographic distance. And it shows that the association between genetic data and geographic distance was only obvious for, let's say, the time that we see the small SNP differences. If we compare in the figure 3a, so we have distance 0 kilometers between 0 and 10, 10 and 15, 15 and 20, 20 to 40, and 40 to 100 kilometers. If we compare these 6 different bar graphs, what we see that the purple color is always constant over these 6, let's say, scenarios. But the only thing that is changed is the proportion of small SNP differences. For example, when the distance is between 0 to 10 kilometers, as we see in the red column that is highlighted here, is the proportion is about the 30%. It's about, it, of course, is in log scale, but what is obvious is that at least in this scenario, when the distance is between 0 to 10 kilometers, the red color is much bigger than the time that we compare the distance between 40 to 1 kilometers. So that's of course obvious. When we have just less distance between 2 different unions, the possibility of finding 2 identical, let's say, parasite with the same genetic structure is much higher compared to the time that we talk about 2 unions or 2 regions that are located 100 kilometers far from each other. So that's why it's mentioned that this graph clearly shows that the geographic distance is only obvious for small SNP differences and not the big and large SNP differences. The next point is that we can interpret the result in such a way that the places that are closer in terms of the distance, of course, we see less variation or less differences in terms of, let's say, their genetic identity. If we look at the figure B, here it shows the genetic mixing index for each location. So it said that the unions that are colored in white are the place that we don't have any genetic data of them, and the places that are colored in gray are the places that they could include the genetic data, but the genetic mixing index that they calculate for such reason for not practical was not identical due to the lack of samples. And again, of course, when the colors change from yellow to red, it means we show higher genetic mixing compared to the place that in red colors we have higher genetic mixing index, suggesting high parasite flow importation compared to the places with yellow colors. So as we see in Southeast Asia or in the forested jungle, so these places, if you merge this picture with the picture that we had in figure 1, we will find that the places that are highlighted in the red colors are the forested region, and we see the majority of, let's say, parasite flow or importation in the places in the forested region compared to the other places, let's say, that they call it non-forested region. And at the same time, they found the high genetic mixing in forested region with a high rate of travels compared to the other places that the rate of travels between 2 unions was not really high. So let's go to figure 4. So the figure 4, let me,
Mahdi?
Yeah.
Maybe if you can wrap up in 2 minutes, maybe just to have a few questions because it's almost the time.
Okay. Yeah, I finish it soon. Okay. So yeah, that is figure 4. Let's see to make sure that okay. So this figure shows that it estimated the people that are not local cases, and let's say somehow they are imported cases based on the data of travel survey and the mobile data. So they mentioned that what we see here, let's say, okay, the number A and the number B. First, let's just start with the number A. The number A is the figure that is created based on the data of the travel survey, and the figure B is this map is created based on the mobile phone data. Again, what we see is totally different patterns of imported and local cases, and I'm not sure which one we should trust it on, but okay, at least this is what they did. So in number A, we have the travel survey data, and the B, we have, let's say, the phone data. And what they found was that they compared, as we see in the number C, so they compared the number of non-local cases based on genetic mixing index. So what we see that, for example, when we use the travel data, they found 40% of the non-local, the median was the non-local cases data was about 40%. But when they use the mobile phone data, the number increases to 80% non-local cases that are shown in red, which means they are somehow, they did not explicitly say that they are imported cases, but they try to put the result of the caution they called the non-local cases. So Christopher, do we still have time for the last figure, or you prefer go to for the Q&A session?
I think we can go for the question. Yes. Maybe.
Okay.
Yeah. Yes. So is there any relevant result that needs to be explained, or?
So this we can explain it in 1 minute because I found it very interesting. It shows the estimate routes of side importations based on the different types of data they have. And the main idea was that what would happen if they integrate the data of, let's say, travel survey data, as it's shown, the figure is constructed based on travel survey data, and the number B is constructed based on the mobile data. In C, they combine both data together to have a better, let's say, resolution. And finally, based on all data that they collected in their study, they came to the figure D. And based on the figure D, they could, let's say, separate the settings of the study in 2 different regions. The blue color indicate the places with genetic index less than 0.1, that is called as, let's say, small genetic mixing, indicating that there is not a lot of parasite transmission from one unions to another unions. And at the same time, they could find another regions that are highlighted, let's say, in a red color, as a place with high genetic mixing index, and it's a places that is forested region with a lot of travels from the pairs of unions. And the main conclusion was that when we integrate all data, the survey data, the phone data, and the genetic data together, then we can have a better understanding about the pattern of transmission, or at least the source and sinks of transmission. So it will help us, let's say, the policymakers to implement better intervention to be able to eliminate area, let's say, in the forested region when we have a lot of travels between one unions to another union. So it was their discussion and the way that they integrate all the data that they had in order to have a clear idea about what is happening in southeast of Bangladesh. Yeah, I think now we can go for the Q&A session, Christopher.
Okay, thank you, Mahdi. ¿Tenemos preguntas para Mahdi?
Christopher, de repente me puedes ayudar un poco con el inglés para preguntar rapidito.
Dale,
¿Por
dale.
qué ellos, cuál fue el criterio que ellos han utilizado de elegir un 17% de SNPs para que sean parásitos similares? ¿Cuál ha sido la razón o el criterio que han utilizado ese valor?
Yes, Magdi, I will translate the question. So what was the criteria to set up this 17.5% SNP threshold for, I think it's for the genetic mixing index?
Yeah, it's a really good question, Christopher. Unfortunately, they did not any, okay, about 75% for SNPs. Okay,
Yes.
let me check, because no, it's not mentioned, it is something else. Let's say the bad point, let's say this article is that they did not mention anything about the way that they choose their cutoff. For example, they mentioned that they consider genetic mixing index less than 0.5 as a neutral and greater than 0.5 as high. But there is no information how they reach to this cutoff. And again, in the question that our colleague asked us, there is no information how they came up with this cutoff.
Yeah, that's a bit tricky, right? Because if there is no information about how they did that, how to follow. Yeah, that was also my question. And the other thing is how, I mean, what was the criteria to select the SNP panel? Because as you said at the beginning, it's very important to have markers that have a very high power for discriminating between imported and local infections. So
okay, again, there is no information how they choose these 100 SNPs. The only thing that they mention is that they also use the drug resistant related markers that are mentioned in supplementary files number 3. But in supplementary files number 3, what you can find is just the drug resistant markers among these 101 SNPs. But there is no information in which chromosome these SNPs are located and for what reasons they selected these SNPs.
But maybe there is a reference for this panel or not? I mean, maybe from a previous work. Maybe.
Okay, as you see here in genetic analysis section, there is only one reference, and this reference refers to, let's say, the way that they calculated or estimated complexity of the infections and the population allele frequency, but there is no information about from which source 100 SNPs
Okay, and do they provide any kind of validation to the method they have developed?
No, there is no kind of validation.
Okay, so no sensitivity analysis or?
No, there is no sensitivity analysis. There is no methodology explaining any possible external validity findings. No, there is no information about validity.
Okay, and do you know if the genetic mixing index has been used somewhere else or after this article or before?
Actually, I didn't check other articles whether they use the same index or not, but what I see here is not a really complicated, let's say, formula. It's just based on that if the probability of genetically similar given, let's say, you are far from each other or you are close to each other. So as we see, it's just based on NFS, NFNS. Okay, you can see everything here. So it's just based on the price of far or close to each other, and then it's just calculated proportion as a kind of probability. And
what I wonder is, for example, if we would like to use this kind of of index. Considering that in the Amazon, in the Peruvian Amazon, you can have like communities that they are in kilometers, they might not be far away, but but there might be like a river, for example, and where there is no much flow among these. But maybe there is another community which is much further than the other one. So then it's tricky because then you're not considering that there might be some barriers that limit the gene flow or the mobility of the human mobility, for example. So I don't know if that's considered in this study.
Yeah, I could get what you exactly mean, but as you see, they considered 7 different geographic distance, and they considered that if 2 unions are 100 kilometers far from each other, so they call it, yeah, they are far from each other. But again, I do not have any idea from which source or references this cutoff comes. For example, from 10 to 15, 15 to 20, and suddenly from 20 to 40 and 40 to 100 kilometers. So as you mentioned, so maybe in one area between 10 to 50 kilometers might be considered very far with no access to unions, without no, let's say, river or routes or roads. So, but in other parts, for example, here, what I understood it is in southeast of Bangladesh, people can easily travel from, let's say, one side of the country to the other side of the country. I don't know, it's because of, let's say, a lot of rivers that they have, or because of, let's say, good transportation route that they have. But I admit that what you said is 100% correct, because what we may see in, let's say, our setting in the Peru might be completely different from what we see here. So maybe in Peru, even 8 kilometers might be considered as really, really far, because there is no connection, let's say, between the two unions or the regions. But in other settings, 8 kilometers may be considered as a close.
There is a question from Luis. So in this case, which gold standard would be ideally, would be the best to use as a validation step?
Okay, what's the best gold standard to? What I see is that they used all the source of information that they had. They used the survey data, phone data, and the genetic data. But I'm thinking.
Yeah, I think maybe it depends. Huh? It depends from which tools you have. Of course, if you, I think from all of these 3, I mean, you have the phone lines, you have the survey, the traveler survey, and you have genetic data, right? But if the travel survey has been done very well, I mean, that might be kind of your gold standard. I think that's why at the end they are comparing the 3 methods and trying to integrate them into one prediction. Yeah. But then because the phone lines, I'm not pretty sure if the cover, I mean, you know, the coverage, it's pretty good and so on. So for sure, in the Peruvian Amazon, it won't work. I don't think so.
Okay.
There is no phone line there.
They use the regions with at least one, let's say, cell phone tower, and they collect the data of 6 months, and they use the average data to have an estimation about, let's say, the number of travels that is happening between 2 different unions. But what I was also thinking is that shouldn't we take the impact of season into account to see whether in which season these trials are happening? Doesn't matter that it's happening in the rainy season or in the non-rainy season.
Yeah, for sure, and also not only related to malaria, but also to the human. I mean, the population's behavior. I think here in the audience, I think a lot of, for example, Mitchell, he knows people. You have to choose when to go into the field, otherwise people will be moving for festivities and things like that. So that's something else. So doing like a cross-sectional study won't work at all on this kind of analysis.
Okay.
But that's something to consider. ¿Hay más preguntas para Mahdi? Are there more questions for Mahdi?
Yes, yes. Hi, Mahdi. Great
Yes,
presentation. This paper is really interesting and also hard because of all the formulas they show. My question is, do you plan to use this methodology for your work?
I'm not going to use, let's say, exactly this methodology for what I want to do in my PhD, but the idea that I choose this, let's say, article, and the reason that motivated me to present this article was a title, because my PhD, the topic of my PhD is also about the human mobility and the impact of human mobility on, let's say, persistence of malaria in remote areas in the Amazons, by using and integrating the parasite genetic data and the human mobility and, let's say, the epidemiological and travel survey data. But to be honest, I expected to see more in this paper, but it was a little bit disappointing. For example, I was looking for a section that gave me an idea about how we can have an estimation about the origin of the infections, and also not only the direction of the infections, but also, let's say, the density of the infection that is carrying from one area to another area. So what I can say that I will use, let's say, the methodology that using this article as much as I can in my study. But I found is that what they did is still far from what we are looking for to do, because in this paper there is no information the way that they use 100 SNPs and how they, let's say, construct their SNP panels. There is no information about what kind of epidemiological model they use. They just generally mentioned that, okay, we integrated all the data that we have to create epidemiological models, but there is no information what kind of model is that, what are the parameters of these models, and how they can interpret, let's say, each one of these parameters. And again, I think what is really important for us to have an idea about, let's say, the way that we can distinguish between the imported cases and the local cases. And as I mentioned earlier, so they try to talk about these sections with a lot of cautions. Sometimes they use local and non-local cases. Sometimes they use local and, let's say, the imported cases. But my feelings is that the authors were not really confident that, at least they know that the method that they used was not 100%, let's not say 100%, but they knew that the method that they used was not really reliable in terms of distinguishing between imported cases and the local cases. However, in the justification, they mentioned that they aim to distinguish between the imported cases and the local cases. But what I saw in the methodology and the results was more like, let's say, a general overview of the, let's say, the connection between the two unions and the similarity that we may find in terms of, let's say, parasite genetic similarity between two different unions. But there is not detailed information about, okay, if we see that there is a, let's say, differences between two unions, then how we can interpret the result, and then how we can say that, okay, what is the index, or let's say, what is the scale that we can say this person with, for example, 10% confidence or 20% confidence is a local infections, or let's say it's a imported infections. So to answer your question, yeah, it's a good article for me to at least work with some formula to see whether I can use it in my, let's say, project. But to be honest, I did not find it very helpful to at least give me some idea about what I can at least add to what I'm currently doing. But since this project is done under the supervision of, let's say, the Harvard University, I think the best thing that I can do is to maybe communicate with the first author or the corresponding author. Maybe they provide us more information, and if I get any more information, of course, I will share it with all of you.
Okay, great. Thanks, Mahdi.
Robertson, do you have another question? I think your
Yes.
raised.
Yes. My last it's our opinion, but the problem with samples that have low parasitemia, for example, in Plasmodium vivax, is very common to see about this case, right? But what's happened with the sample with it's not possible the genotypification with the SNPs. You can see maybe another result, because there are other population that you can see how is this parasite, right? Maybe it's a limitation this article.
So if do you mean that what would happen if we take the role of other parasites into account, like vivax?
Yes, vivax we have a low parasitemia, right? It's but I don't know if there are information about a parasite that with low parasitemia.
So at least they didn't mention anything about this issue in their paper, but it's also a good question because they only considered the P. falciparum and not, let's say, the other parasites. And as we see here, we also have the mixed infections. I don't know if this is the case in Peru or not, but if this is the case and if it is frequent cases, so the scenario becomes even more complicated. But I think they just the reason that they choose just falciparum was that to make everything straightforward. And another reason is that if you compare the number of people infected with falciparum, it's almost 5 times greater than the number of infected with vivax. So in order to improve the power of the study, so I think that's another reason that they shifted from the vivax to the falciparum. But you also, if I'm not mistaken, you in some parts of your question, you said something about, let's say, the SNPs and the genetic panel. I'm not sure if I could understand that part of your question clearly. Can you just repeat it again? What was the point about SNP panels? Or
Yes.
so I cannot hear you. I had your voice, but it's gone. Christoph, I think there is a problem from my side because I cannot hear any.
Robertson?
Yes. I didn't hear very well. Sorry.
¿Puedes repetir tu pregunta?
Right. Okay. What's happened with a population with low parasitemia? Right, is not possible to see in this article, because I understand that the sample was collected with hospital maybe, but in the other case, for example, asymptomatic with low parasitemia, it's not possible to genotyping. This is the problem with IVAX.
I think I think it's a kind of, let's say, the selection bias that we always face. So I there is no other way to make sure that we collect all available cases, either they are symptomatic or asymptomatic. So here they just use the, let's say, symptomatic cases that refer to the, as you mentioned, refer to the clinical setting, hospitals, or I don't know, anywhere else. So I think that is always a problem. So what we can do, I think it may not be feasible to collect all available persons. So, but we can always implement some solutions to make sure that we collect as much as data that we can. As you know, in the rural area and remote area, it's not easy to, let's say, follow up the peoples or do, let's say, for example, the clinical test to see whether this person is infected or not. So what we routinely do, as we all of us know, is that we first refer to the persons that refer to the clinics or, let's say, the clinical settings. But in order to take the asymptomatic person into account, I think it's still a challenge, because it's really time consuming and, let's say, financial demanding to be able to, for example, take the blood tests from all the people that we know that they are living in an endemic region. And we guess that maybe many of them are, let's say, the carriers or infected people. But for so many reasons, for the logistic regions, for, let's say, the financial issues, of course, it's not always to collect all blood samples. I'm still thinking what we can do to reduce the selection bias. Maybe what we can do is that, of course, we take all the people that take into account all the people that refers to the clinical setting with some clear symptoms that indicating that these people is infected with malaria parasites. At the same time, maybe if we have enough time and if we have enough financial means, we can randomly, for example, choose 20% of the, let's say, overall population to see whether we can detect any sign or signals of the presence of the parasites in the blood samples, even though the people are asymptomatic. What I want to say that in any kind of epidemiological study, we have a source of biases. We cannot completely eliminate the source of biases, but we as researchers must, as you mentioned, we must carefully think of it and always find a solution to, we can make it as low as possible.
Okay, thank you, Meli, for your answer.
Welcome.
Okay, I think we don't have any other question. Thank you, Mary, for your presentation. It was an interesting topic. Thank you, everybody, for attending.
Yeah, and thank you to all of you for attending these sessions. Thank you so much for your time.
Okay, creo que podemos dar por terminado.
Gracias, Eric.
Thank you.
Thank you, Mari. Great presentation.
Okay, welcome. Okay, see you in next session.